All right. We are going to continue on our journey with graphs, but I'd like to follow up with what I hope that you did last night. Um, First off, the cosine graph. You can take a peek. Did you see the same thing? Okay, you'll notice that what I'm drawing with the cosine graph starts at x equals 0, y equals 1. So I'm choosing that as my starting point because I actually want to highlight that is going to be important. The graph of cosine starts up at 0, 1. And then if I want to draw one period, which you're seeing one period here, I get back to the starting point. I get back to the top. Okay. Sometimes kids will say, well, cosine's the same as sine. Yeah, it's got the same answers here, but it starts at a different spot. That's going to be like a key idea that I'll even highlight today. Okay, now you can have more of the cosine graph graphed. Okay, you can have more of it, but I kind of want you to focus on that first positive period. So there's your cosine. Um, by the way, if you have any questions about what you're seeing, I'm more just kind of delivering the facts right now. But if you aren't sure how to get them or have a question if yours was different, here's secant. I happen to have it up on the screen. Secant got a little more going on, okay? But if you kind of focus on certain parts, you can see that we have a positive wave, we have this negative wave. We need both the positive and the negative to make one period. That's what I'm trying to highlight down here. This stretch from negative 90 to 270 is one period. By the way, you could see one period other places. Okay, you could see one period by looking at this bottom and then this top one. That's still 360 degrees. Okay, the domain, how'd that go for you? It's a formula using the K notation. And then you can see the range. Okay, you can give the answer as an inequality. You can give the answer as an interval using parentheses and infinity, like we did yesterday. I'm trying to show you some different options. Brandon?
My domain, I have 180K and I have minus.
Yep, you're good. All you're kind of doing is, you're going 180 degrees and then you're taking away 90. It kind of shifts you backwards. Okay, that is fine. Anything else with secant? Remember, if you're saying, should I memorize this? Well, as you spend time in class, you're going to get to know these graphs, and I'm going to be highlighting different parts of them. So you don't necessarily have to memorize them. We're going to get to know them. And here's cotangent. Cotangent's a little different than tangent. Okay, notice that the direction of the graph, it's falling, it's going down sort of in the opposite way. Notice that the asymptotes are at a different spot than tangent. Okay, again, just stuff to notice. But the period is the same. It's the distance between one set of asymptotes. And then we have our domain using the K notation. Again, this is kind of the facts. Do you have any questions on how to get them? Okay, I encourage you to have all 6 of them available in your notes. You'll notice I didn't check the homework. As always, that doesn't mean it wasn't important. Okay, it was just that today I decided just to go over it with you. What we're going to do today is talk about transformations. We're going to talk about transformations. Basically, a transformation is a change. It's a change. You actually study transformations in an algebra class. So you might feel like as we start to look at these transformations that there's some similarities. I don't want to say that you've heard it before, but definitely some similarities with algebra. Now, the way I like to conduct this is instead of me just telling you, hey, kids, if this, then that, I want to let you discover it a little bit. I want to let you explore it. So I'm going to give you some graphs. I'm going to give you some equations. where I'm going to encourage you to, as I like to say, consider them, which means look at them. When you look at them, what you want to ultimately try to figure out is what has changed. What word would you use? Okay, so this box over here, if you're a student, you can create this in your notes. Please know that I'm going to be changing these equations a couple times during the period. So this box is kind of meant to get you guys to discover something. Some students jot it down, some students just kind of participate. When we're done, we will come up with a rule. That I hope you will write down. We'll have a rule, and I'm just kind of using this box format if you choose to do the same thing. Remember, our goal is to see and understand the transformation today. To see the transformation. Okay, and then eventually we'll learn how to use the rule. Actually, the rules are pretty easy, but it's also important for you to kind of discover them. Now, if you're going to play along, I encourage you to type in these three equations. You can actually type in all three of them. Remember the stuff we did yesterday? Remember how to get your calculator kind of set up to be able to accept these three equations. Make sure you're in degree mode. If you're borrowing a calculator from me, make sure it's in degree mode. Obviously, the first graph is the good old sine wave. Sometimes we call that the parent graph. The parent. And then we have a 2 sine and a 4 sine. What has changed? Don't forget, Zoom Trig is a friend of yours. Zoom Trig will help to set up the window. This one's kind of the freebie. This is supposed to be the one that everybody looks at and says, I know what changed. What has changed? What do you observe here? How about for 2 sine? Do you remember which one it was? Right? And now the amplitude is equal to 2. Again, just visually, you guys should be able to look at that graph and say, yep, it is now going to a height of 2, or maybe you could say it's dropping down a height of 2. Amplitude's always positive, so we don't say negative 2. So the 4 sine, it has an amplitude of 4. When you multiply a coefficient, onto sine or cosine, you change the amplitude. Oh, and by the way, what's the amplitude for this parent graph? It's still the coefficient. Okay, but we have our first rule. And this is where, if you want to use the little box style here, you might say amplitude. Notice that I'm telling you that it will be a sine or a cosine. I'm trying to expose you guys to some different notation. It says a sine of theta. Yeah, you can put like a theta in there. Students tend to like the letter X, but I'm going to expose you to theta. It's just the variable. It's the independent variable. But real simply, the absolute value is the amplitude. The absolute value is the amplitude. Now look, I want math to be more than rules. And you're a smart group. What's really happening here is we're multiplying the y value. Like if you multiply a number in front of an equation, you're multiplying all the y values by that coefficient. What happens if you multiply y values? Well, they obviously change. In this case, they get bigger. because I'm multiplying by a bigger number. Okay, so we're seeing the graph's y values expand. Let's take these three equations and consider so we've got cosine this time. I'm doing the cosine of 4x. I'm doing the cosine of a half x. Now, if you're writing them down, great. When you get ready to put them in your calculator, a little suggestion from the teacher, I might suggest that you graph these two. Take a look. Then graph these two. Take a look. I'm suggesting that you not graph all three of them at the same time because it gets all goofy. It might be hard to figure out what's going on. Cosine of 4x. What has changed? Cosine of a half x. What has changed? Again, you do what you want, but you don't need to graph all of them at the same time. It's cool if you're trying to write down the observation on your own. Maybe you're just thinking about it, but in all seriousness, how would you explain what you see? I know every one of you would look at that and say, yeah, that looks different. Well, what's different about it? Like, it's always neat to hear it in your words. The period is different. Okay, we're definitely getting warm here because you're exactly right. The period is different. Again, in your own words, or do you want to add something to this? Like, what is the period? Or in your own words, what else is different? Now, do we feel like the period has gotten bigger or smaller? It's definitely gotten smaller. Okay, there's more graph squeezed into a smaller space. Good.
So you divide the original period by whatever the number is.
Okay, so you divide the original. This sounds pretty juicy. You divide the original period by whatever this number is. Like, what would that be for this problem?
365 by 4.
Okay, so 365 by 4, 90. Now, everything that's been said is exactly right. Great job. Like, let me show you something. Okay, kind of going back a step. Some of you, actually all of you, you need to be able to see a period. And this is some new territory now. So just kind of look, because you guys are going to need this skill in the next coming days. To find a period, all you need is a starting point. Now, I happen to kind of sort of zero in on that y-intercept. And then you need to be able to go through a full cycle and ultimately end up at the same point. In other words, back at a maximum. So those two red dots and the distance between them represents one period. Well, you've got a calculator. You can trace. If I trace, I see that the first dot is obviously at 0, but the next dot is at 90. Now notice what I'm looking at. I'm looking at the x values when I say stuff like 0 to 90. And so that looks exactly like this period of 90 that came from the original period divided by that number. We're going to call that number k. Could be called any letter, but I'll show it to you as k. So are you trying to apply what you heard to the 1/2, the cosine of 1/2 x? What has changed? The period. What is the period? Is it bigger, smaller? Bigger. Okay. What about this thing about the original period divided by that number? What's 1/2? What's 360 divided by 1/2? Right, 720. It's the same as multiplying by 2, but this is good stuff because look, it is 700. Now this is a skill that you guys will need to be able to look at a graph and say, okay, between those 2 points is one period. Okay, somebody says, how did you know to pick those 2 points? Well, because they're 2 points that get me back to where I started. Here I'm at a bottom, and I get back to the bottom. And get to know your calculator, because out here is negative 360, and out here is 360. Don't worry if maybe you didn't come to class knowing all that, but negative 360 to 360, bingo, 720. Let me help you organize the rule. Again, if you want to put a box around it, do something to kind of highlight this. This is the rule for period. So if you have a sine of k theta, a cosine of k theta, and it was said real well by your classmate here, nice job, the period is going to be the original period divided by k. Again, really nice job. Sometimes people say the new period. If you want to emphasize that it's the new period, it's going to be the original period, 360 divided by k. So how about tangent kind of hanging out here by itself? We didn't look at it up on the screen, but can you adapt the rule? This time you would be taking what divided by k? This time you'd be taking 180. 180 would be the original period divided by k. Now we're using the calculator to help discover things, but we're also realizing that we're discovering these things so we can take the calculator away. I don't want you to type this in your calculator yet. Let's just think about what was just said. We have a nice little rule. So if you trust it, the new period now would have to be 180, because that's the original period, so it'd have to be 180 divided by k. Okay, it's not supposed to be a hard math problem, just kind of giving you a chance to process this. And now I'd like you to see a period of 360 on a tangent graph. Okay, at least for the sake of what we're doing today compared to yesterday, we haven't seen this yet. You guys haven't seen a tangent graph with a period of 360. what do you think this is going to look like? Feel free to play along, or I'll show you up here. But again, I just want you to see this. By the way, the reason I want you to see it is eventually you guys are going to be drawing these things. You're going to be drawing them without the calculator. Remember what the original tangent graph looked like? Okay, you see now what happens when the period gets bigger. Okay, the period gets bigger. We also have a change in the position of these asymptotes. Just some stuff to kind of experience. If you want to sketch this in your notes, you can, but if you just want to kind of watch, what I hope you're thinking about right now is what's the value of those asymptotes? Now, you can just get the value by looking at the graph, but think about it a little bit. What's the value? So the one out to the left, the negative one, is at negative 180. The one to the right, the positive one. Now, what does this confirm? Like, what do you notice about the space between those asymptotes? And this is how this works. The space between the asymptotes is the period for a tangent graph, okay? Because that's what it takes to see one cycle. Just by the way, this x-intercept out to this next x-intercept would be 360, okay? There's other ways that you can see a period. You can go to like the next equivalent point. All of these things are good. Okay, this is the way it's supposed to work. Another transformation. Excuse me. I'm going to go back to sine. By the way, you may not feel like you have to graph that anymore. You might want to just get right down to the transformed graph. The sine of x plus 60. Notice that the plus 60 is with the x. So again, the sine of x plus 60. And then y equals the sine of 2x plus 60. Now, if it was me, I would just graph x plus 60, the sine of x plus 60. Just graph that, sit on it a little bit. What do you notice? And then graph the 2x plus 60. Again, try to sit on the x plus 60, maybe long enough that you even realize, oh yeah, this is what changed. Again, try, be thinking. Don't just kind of be waiting for someone to say the answer. Try to be thinking. If you want to write it down, if you want to talk about it. And then how about the third equation? Does it match with what you're thinking? I'm going to choose to go back to the x plus 60. If you want to type it in again, or if you just want to look up here. But what I'm really curious is, what do you see that changed? I won't put you on the spot and call on you, but what do you see that changed? Good. Thank you.
Oh, the line, this is like math, so like the line normally crosses at 0, 0, but now it's crossing at negative 60 degrees.
Okay, so I'm just repeating it. The line normally crossed at 0, 0. Now it's crossing at negative 60?
Yeah.
Now,
yeah.
Now there's a point that you're looking at. Short of having you come up and point at it, I'm going to show, because I can tell where you're looking. This point right here is in a new place. Again, to paraphrase what Brandon said, it's used to be at 0, 0. Now it's at negative 60. Something to add to that, something different. Again, I won't put you on the spot, but if you want to volunteer. Okay. What I'll add to what was said is that every point has actually moved to the left 60 degrees. Okay, I like the point that you picked because it actually is the point that the teacher kind of uses. But every point on this new sine wave is to the left 60 degrees. We call that a phase shift, or just short shift. We might say shift. You'll hear me say phase shift up in the notes. Now let me just highlight that point one more time. You might not realize how important it is just today, but boy, as we keep going through the next couple of days, that point was what you'll hear me say is the original y-intercept. Process what I just said. That point right there is the original y-intercept. Now, if you're like, no, that's not a y-intercept, that's an x-intercept. I know, but I'm talking about the original y-intercept. So what you have to do is you have to be able to picture the sine wave. And this is the part where you want to get to know these graphs. You want to picture the sine wave and its original y-intercept. It has moved to the left 60. Okay, so again, that's good stuff. Now, this is about as tricky as it gets today. That doesn't mean that you won't understand it, but there's a couple things going on at one time. What do you think? Go ahead. All right, so the shift is, I'm going to just repeat, is still to the left 60, but the period's 180. Okay? One of the things you said is 100% right. One of the things you said is on the right track. Okay. Now, again, are your eyes kind of focusing on that point? Obviously, if I plot it, they do, but that point is the shift point. It's the original y-intercept. Now, you made a quick change, which was good. Don't be scared to play around with your calculator. If you're like, how do you know that that's 30? I mean, how'd you know it was 30? You just kind of, it just looks like 30, okay? Don't be scared to trace. You can trace along these graphs and you'll land on these points. I'm never going to give you points of odd increments. They're always going to be points that you can find. So push the trace button and confirm that the graph shifted to the left 30. By the way, the statement that was said about the period equaling 180, nice job. That's dead on. So what's kind of the deal here? Okay, what's the deal? We want to get the idea that we're shifting. And by the way, nobody sort of bucked at the idea that we're shifting to the left. But remember from algebra that when you have a plus sign, it's like the opposite. So that plus sign is why we're going to the left. But how come it was 60? How come it's 30? You know, what is the connection between these numbers? Okay, and real simply, well, that actually is true. Okay, yes, that actually is true. I would like us to say more that the shift got cut in half because we're dividing these numbers. They say, well, isn't that what would happen all the time? Yes, this number becomes a divider all the time, but kind of keep them separated. The shift came from dividing these numbers. The period came from the last rule where we were dividing by k. So yeah, we actually have like an interaction between both of these numbers. So we call this a phase shift. It works for sine, cosine, and tangent. Kind of feels like you're writing that down 3 times. You can abbreviate your notes if you want to. But I want you to get the idea that it works for all 3 of them. And it's as simple as c divided by k. C divided by k. Pay careful attention to my language here. I mean what I'm saying. It's a horizontal shift of the original y-intercept. You might want to put the word original in there if you choose. It's a horizontal shift of the original y-intercept. And as a gentle reminder, positive actually does shift to the left and negative actually does shift to the right. With the time that we have, we'll be able to kind of equation. And some of your homework, this is what all you're going to do. You're going to take an equation. You're going to use these 3 rules. Bam, bam, bam. You sort of pop out your answers. What I also would like to do is try to get you guys to see these things on the graph, because eventually the more you see on the graph, the more you'll be ready for the next thing. But if I give you 2 tangent of 3x minus 90, it actually can be pretty simple to sort of bang out these answers. Again, just using our rules. Just kind of pausing if you want to think about it a little bit. We're going to have to do the answers here shortly. Don't be stumped on amplitude for too long. Tangent does not have amplitude. So if you wrote down the number 2, that was kind of meant to make sure that you don't do that again. Now, if you're saying, what does the number 2 do? It just kind of stretches the graph a little more. It just kind of like doubles the graph, but there's still no amplitude by definition. How about period? Original period divided by k. That's all there is to it. 180 divided by 3 gives you 60. And how about the shift? Well, you have a minus sign, so you would say to the right, 90 divided by 3, which of course is 30. I wrote the word right twice. What I'm doing right now is more to help you for our next thing, but at least look at it. Because sometimes people are like, whoa. Okay, there's some stuff, though, that we can like focus on. The point that I already plotted happens to be one of them. Well, or the one right here. Both of these red dots are 30 degrees. Of course, the one is 30 degrees to the right. Okay, the other thing about those two dots, since we have them one here, is how far apart are they? Well, they're 60 degrees apart. So it's kind of a goofy graph, but it matches our answers. There's even asymptotes on there, which I'm not going to get into, but they would also fit with these ideas. Homework helper, remember that's on Google Classroom, and it'll give you a chance to practice this.